91 Functions for the master, closures and scopes closely tied to the functions we learned about in previous chapters. Closures are a defining feature of JavaScript. Although scores of JavaScript developers can write code without understanding the benefits of closures, their use can not only help us reduce the amount and complexity of code needed to add advanced features, but also enable us to do things that otherwise wouldn't be possible, or would be too complex to be feasible. For example, any tasks involving callbacks, such as event handling or animations, would be significantly more complex without closures. Others, such as providing support for private object variables, would be outright. This chapter covers using closures to simplify development, tracking the execution of JavaScript programs with execution contexts, tracking variable scopes with lexical environments, understanding types of variables, exploring how closures work. 92 Chapter 5 Functions for the master, closures and scopes impossible. The landscape of the language and the way we write our code is forever shaped by the inclusion of closures. Traditionally, closures have been a feature of purely functional programming languages. Seeing them cross over into mainstream development is encouraging. It's common to find closures permeating JavaScript libraries, along with other advanced code bases, because of their ability to drastically simplify complex operations. Closures are a side effect of how scopes work in JavaScript. For this reason, we'll explore the scoping rules of JavaScript, with a special focus on recent additions. This will help you understand how closures work behind the scenes. Let's jump right in. How many different scopes can a variable or method have, and what are they? Do you know? How are identifiers and their values tracked? What is a mutable variable, and how do you define one in JavaScript? 5.1 Understanding closures. A closure allows a function to access and manipulate variables that are external to that function. Closures allow a function to access all the variables, as well as other functions, that are in scope when the function itself is defined. Note you're probably familiar with the concept of scopes, but just in case, a scope refers to the visibility of identifiers in certain parts of a program. A scope is a part of the program in which a certain name is bound to a certain variable. That may seem intuitive until you remember that a declared function can be called at any later time, even after the scope in which it was declared has gone away. This concept is probably best explained through code. But before we get into concrete examples that will help you develop more elegant animations in code or to define private object properties, let's start small, with the following list. Var outer value equals ninja, function outer function, assert, outer value equals ninja. I can see the ninja, outer function. In this code example, we declare a variable outer value and a function outer function in the same scope, in this case, the global scope. Afterward, we call outer function. Listing 5.1 A simple closure defines a value in global scope, declares a function in global scope, executes the function. 93 Understanding closures. As you can see in figure 5.1, the function is able to see and access the outer value variable. You've likely written code such as this hundreds of times without realizing that you were creating a closure. Not impressed? Guess that's not surprising. Because both outer value and outer function are declared in global scope, that scope, which is a closure, never goes away, as long as our application is running. It's not surprising that the function can access the variable, because it's still in scope and viable. Even though the closure exists, its benefits aren't yet clear. Let's spice it up in the next listing. Var outer value equals samurai, var later, function outer function, var inner value equals ninja, function inner function, assert, outer value equals samurai, I can see the samurai, assert, inner value equals ninja, I can see the ninja. Later equals inner function, outer function, later. Let's overanalyze the code in inner function and see whether we can predict what might happen. The first assert is certain to pass, outer value is in the global scope and is visible to everything. But what about the second assert? We're executing inner function after outer function has been executed via the trick of copying a reference to the function to the global variable later. Listing 5.2 Another closure example. An empty variable that we'll use later declares a value inside the function. This variable's scope is limited to the function and can't be accessed from outside the function. Declares an inner function within the outer function. Inner value is in scope when we create this function. Stores a reference to inner function in the later variable. Because later is in the global scope, it'll allow us to call the function later. Invokes outer function, which causes inner function to be created and its reference assigned to later. Invokes inner function through later. We can't invoke it directly because its scope, along with inner value, is limited to within outer function. Figure 5.1 Our function has found a ninja.
You know the guy that we know from Game of Thrones? They were supposed to make a sequel about this, but about his time as Pharaoh, because he becomes Pharaoh not right after.
What guy from Game of Thrones?
The guy that got locked the guy that got locked in the vault. The one who's general. First, the guy who they call Vizier, because all these people, this is why they think that he was murdered, because so many people was gunning after his kingdom, that they have written evidence of, like not written, but like hieroglyph evidence of. But they can't take the evidence really as proof either, because it was written like 50 years after the event. But what they do have first-hand depictions of, which is what favorite parts of it is his battles. Actually, he did innovate stuff. He innovated war stuff, like war chariots and stuff. He had to design. He learned how to design war chariots, and he designed his own war chariots. He got his legs so that he would ride better. I learned that about him. They got Ridley Scott in this. Well, they got him to direct one episode of this. I might not like all of Ridley Scott's ideas, but I like his depictions of history. Especially his depiction of our history in the time his first-hand account of like the Cold Wars and stuff. Being a kid and having to go underneath the desk and everything. I like those depictions that he was putting in some of his movie documentaries.
Who was hiding in plain sight. 94 Chapter function is running. It's not surprising that the function can access the variable, because it's still in scope and viable. Even though the closure exists, its benefits aren't yet clear. Let's spice it up in the next listing. Var outer value equals samurai, var later, function outer function, var inner value equals ninja, function inner function, assert, outer value equals samurai, I can see the samurai, assert, inner value equals ninja, I can see the ninja. Later equals inner function, outer function, later. Let's overanalyze the code in inner function and see whether we can predict what might happen. The first assert is certain to pass, outer value is in the global scope and is visible to everything. But what about the second assert? We're executing inner function after outer function has been executed via the trick of copying a reference to the function to the global variable later. Listing 5.2 Another closure example. An empty variable that we'll use later declares a value inside the function. This variable's scope is limited to the function and can't be accessed from outside the function. Declares an inner function within the outer function. Inner value is in scope when we create this function. Stores a reference to inner function in the later variable. Because later is in the global scope, it'll allow us to call the function later. Invokes outer function, which causes inner function to be created and its reference assigned to later. Invokes inner function through later. We can't invoke it directly because its scope, along with inner value, is limited to within outer function. Figure 5.1 Our function has found the ninja, who was hiding in plain sight. 94 Chapter 5 Functions for the master, closures and scopes. When inner function executes, the scope inside the outer function is long gone and not visible at the point at which we're invoking the function through later. So we could very well expect assert to fail, as inner value is sure to be undefined. Right? But when we run the test, we see the display in figure 5.2. How can that be? What magic allows the inner value variable to still be alive when we execute the inner function, long after the scope in which it was created has gone away? The answer is closures. When we declare inner function inside the outer function, not only is the function declaration defined, but a closure is created that encompasses the function definition as well as all variables in scope at the point of function definition. When inner function eventually executes, even if it's executed after the scope in which it was declared goes away, it has access to the original scope in which it was declared through its closure, as shown in figure 5.3. That's what closures are all about. They create a safety bubble of the function and the variables in scope at the point of the function's definition, so that the function has all it needs to execute. This bubble, containing the function and its variables, stays around as long as the function does. Although all this structure isn't readily visible, there's no closure object holding all of this information that you can inspect. Storing and referencing information in this way has a direct cost. It's important to remember that each function that accesses information via a closure has a ball and chain attached to it, carrying this information around. So although closures are incredibly useful, they aren't free of overhead. All that information needs to be held in memory until it's figure 5.2. Despite trying to hide inside a function, the ninja has been detected. Function inner function, function outer function var outer value var later var inner value figure 5.3. Like a protective bubble, the closure for inner function keeps the variables in the function's scope alive for as long as the function exists. 95. Putting closures to work. Absolutely clear to the JavaScript engine that it's no longer needed, and is safe to garbage collect, or until the page unloads. Don't worry, this isn't all that we have to say about how closures work. But before exploring the mechanisms that enable closures, let's look at their practical uses. 5.2. Putting closures to work. Now that we have a high-level understanding of closures, let's see how to put them to work in our JavaScript applications. For now, we'll focus on their practical aspects and benefits. Later in the chapter, we'll revisit the same examples to see exactly what's going on behind the scenes. 5.2.1 Mimicking private variables. Many programming languages use private variables, properties of an object that are hidden from outside parties. This is a useful feature, because we don't want to overburden the users of our objects with unnecessary implementation details when accessing those objects from other parts of the code. Unfortunately, JavaScript doesn't have native support for private variables. But by using a closure, we can achieve an acceptable approximation, as demonstrated by the following code. Function ninja, var feints equals 0, this dot get feints equals function, return feints, this dot feint equals function, feints plus plus, var ninja 1 equals new ninja, ninja 1 dot feint, assert, ninja 1 dot feints equals undefined, and the private data is inaccessible to us, assert, ninja 1 dot get feints, equals 1, we're able to access the internal feint count, var ninja 2 equals new ninja, assert, ninja 2 dot get feints, equals 0, the second ninja object gets its own feints variable. Listing 5.3 Using closures to approximate private variables defines the constructor for a
Do they make people just lay on slabs and act like they're not breathing? When you got to pay a dead person?
Yeah, I guess so.
Or do they make a cast of that after they got
No. You can still see the organisms.
And he's been really good at this.
There's a lot of people that do that.
Like the guy who's playing the people who play dead on there's they do really good. I don't be seeing that happen.
Ninja declares a variable inside the constructor function. Because the scope of the variable is limited to inside the constructor, it's a private variable. We'll use it to count how many times the ninja has fainted. Creates an accessor method for the faints counter. Because the variable isn't accessible to code outside the constructor, this is a common way to give read-only access to the value. Declares the increment method for the value. Because the value is private, no one can screw it up behind our backs, they're limited to the access that we give them via methods. Now for testing, first we construct an instance of Ninja. Calls the faint method, which increments the count of the number of times that our Ninja has fainted, verifies that we can't get at the variable directly. We were able to change the private variable, even though we had no direct access to it. When we create a new Ninja 2 object with the Ninja constructor, the Ninja 2 object gets its own faints variable. 96 Chapter 5 Functions for the master, closures and scopes. Here we create a function, Ninja, to serve as a constructor. We introduced using a function as a constructor in Chapter 3, and we'll take an in-depth look in Chapter 7. For now, recall that when using the new keyword on a function, a new object instance is created, and the function is called with that new object as its context, to serve as a constructor to that object. So this within the function refers to a newly instantiated object. Within the constructor, we define a variable to hold state, faints. The JavaScript scoping rules for this variable limit its accessibility to within the constructor. To give access to the value of the variable from code that's outside the scope, we define an accessor method, getFaints, which can be used to read the private variable. Accessor methods are frequently called getters. Function Ninja, var faints equals 0, this dot get faints equals function, return faints, this dot faint equals function, faints plus plus, an implementation method, faint, is then created to give us control over the value of the variable. In a real-world application, this might be a business method, but in this example, it merely increments the value of faints. After the constructor has done its duty, we can call the faint method on the newly created Ninja1 object, var Ninja1 equals new Ninja, Ninja1.faint. Our tests show that we can use the accessor method to obtain the value of the private variable, but that we can't access it directly. This prevents us from being able to make uncontrolled changes to the value of the variable, just as if it were a true private variable. This situation is depicted in Figure 5.4. Using closures allows the state of the Ninja to be maintained within a method, without letting it be directly accessed by a user of the method, because the variable is available to the inner methods via their closures, but not to code that lies outside the constructor. This is a glimpse into the world of object-oriented JavaScript, which we'll explore in greater depth in Chapter 7. For now, let's focus on another common use of closures. 5.2.2 Using closures with callbacks. Another common use of closures occurs when dealing with callbacks when a function is called at an unspecified later time. Often, within such functions, we frequently 97 Putting closures to work. Need to access outside data. The following listing shows an example that creates a simple animation with callback timers. div id equals box1 first box slash div script function animated, element id, var element equals document dot get element bid, element id, var tick equals 0, var timer equals set interval, function, if, tick 100, elem dot style dot left equals elem dot style dot top equals tick plus px, tick plus plus, else clear interval, timer. Listing 5.4 Using a closure in a timer interval. Callback var Ninja var faints. The object instance is visible via the Ninja variable. In the outer scope, we have no access to faints. The faints method has access to the faints variable, as it's within the closure. Ninja instance faint function, figure 5.4. Hiding the variable inside the constructor keeps it invisible to the outer scope, but where it counts, the variable is alive and well, protected by the closure. Creates the element that we're going to animate inside the animated function, we get a reference to that element. Establishes a counter to keep track of animation ticks, steps, a built-in function that creates and starts an interval time. timer. 98 Chapter 5 Functions for the master, closures and scopes. Assert, tick equals 100, tick accessed via a closure. Assert, element also accessed via a closure. Assert, timer reference also obtained via a closure. 10. Animated, box 1, /script. What's especially important about this code is that it uses a single anonymous function, placed as a set interval argument, to accomplish the animation of the target div element. That function accesses three variables, tick, and timer, via a closure, to control the animation process. The three variables, the reference to the DOM element, the tick counter, tick, and the timer reference, timer, all must be maintained across the steps of the animation. And we need to keep them out of the global scope. But the example will still work fine if we move the variables out of the animated function and into the global scope. So why all the arm flailing about not polluting the global scope? Go ahead and move the variables into the global scope and verify that the example still works. Now modify the example to animate two elements, add another element with a unique ID, and call the animated function with that ID right after the original call. The problem immediately becomes obvious. If we keep the variables in the global scope, we need a set of three variables for each animation. Otherwise, they'll step all over each other, trying to use the same set of variables to keep track of multiple states. By defining the variables inside the function, and by relying on closures to make them available to the timer callback invocations, each animation gets its own private bubble of variables, as shown in figure 5.5. Without closures, doing multiple things at once, whether event handling, animations, or even server requests, would be incredibly difficult. If you've been waiting for a reason to care about closures, this is it. This example is a particularly good one for demonstrating how closures are capable of producing some surprisingly intuitive and concise code. By including the variables in the animated function, we create an implied closure without needing any complex syntax. There's another important concept that this example makes clear. Not only can we see the values that these variables had at the time the closure was created, but we can update them within the closure while the function within the closure executes. The closure isn't just a snapshot of the state of the scope at the time of creation, but an active encapsulation of that state that we can modify as long as the closure exists. After 100 ticks, we stop the timer and perform tests to assert that we can see all relevant variables needed to perform the animation. The set interval duration, the callback, will be called every 10 ms. Now that it's all set up, we set it in motion. 99 Tracking code execution with execution contexts. Closures are closely related to scopes, so we'll spend a good deal of this chapter exploring scoping rules in JavaScript. But first, we'll start with the details of how code execution is tracked in JavaScript. 5.3 Tracking code execution with execution contexts in JavaScript. The fundamental unit of execution is a function